Welcome back to another engineering skills tutorial. In this one, we're going to build an analysis pipeline for 3D grid shell structures that uses OpenSeesPy and Blender. You can read a detailed step-by-step guide on this build and download the associated Jupyter notebook and Blender file over on engineeringskills.com. So just follow the link below for that. There's a really detailed step-by-step walkthrough guide on the whole project over there. Now, the other thing to say is good examples of OpenSeesPy code for 3D frame structures are pretty hard to come by online. So even if you're not that interested in grid shell structures specifically, you should find the code that we write in this build to be a really handy reference. Okay, so let's get into it. So in this project, we're going to use Blender to recreate the hanging chain form finding models that would have been used by Gridshell and tensile structure pioneers like Frey Otto and Heinz Eisler. So for this, we'll use Blender's physics engine to essentially simulate a hanging mesh. We can then take this hanging mesh, invert it, and that will become our candidate geometry for our grid shell structure. So I'm over in a fresh Blender file now. So what we're going to do in this tutorial is focus on a relatively simple grid shell structure. Of course, all of the steps that we do in this tutorial you can apply to a more complex structure, but for the purposes of just demonstrating the workflow here, we're just going to keep it relatively simple with our structure. So I'm going to get or generate a grid shell that is 10 meters by 10 meters on a 1 meter grid. That's going to be our flat cutting pattern is what it's known as. We'll apply a physics simulation to that and essentially cause that to drape down. This is the hanging chain part, and then we will apply that simulation and essentially lock in that geometry. We'll invert that structure and then we'll export that geometry. So let's get started here then. So I'll start off by adding a mesh plane. Go into top down view. I will scale that by 5. Go into edit mode and subdivide it by, let me see how many times, it's going to be 9, isn't it? Yeah, 9. Okay, so now I'm going to delete the faces, and that just leaves me essentially with my mesh that we're going to essentially let fall or hang down. Now to do that, we'll do a physics simulation on this, but we have to specify the points that are going to be pinned, essentially what will be our support points. So that's going to be the 4 corners for our simple grid shell here. So I've selected the 4 corners, and over in the data tab, I'm going to create a new vertex group. I will call it pins, and I will assign the selected vertices to that group. Okay, so if I deselect, or rather deselect here, and then if I hit select again, you can see we've selected the correct vertices and they are assigned to that group pins. Next up, we're going to jump over to the physics tab. So I'm going to go out of edit mode first of all, then I'll go over to the physics tab and I'll add a cloth physics modifier. Now when we add this modifier, we get a huge number of additional options here to tweak and to change. Now I'm not going to really deal with any of these. I'm just going to, the main one that we're going to focus on is the vertex mass here. That is the thing essentially that within the physics simulation controls the degree of stretch, I suppose you'd say, of this mesh. Because it's increasing the mass of the vertices in the physics simulation. So obviously the more mass we have, the more this thing is going to hang down, and you'll see that now when we run some simulations. So in the over here, we're going to say we could leave that as 0.3. I'll leave it as 0.3 and you can see what it does. Let me see. I'm going to ignore all of these different settings because really we're not that interested in the details of these settings with the exception of vertex mass, because all this is being used as is a means of generating our hanging chain geometry. The actual structural analysis of that geometry will happen over in our notebook with OpenSees. So to get this thing running, I need to specify my supports, right? So I'm going to come on down to, I'll collapse cache there, I don't need that. So come on down to shape, and within shape, within pin group, I'm going to select the vertex group pins which I created earlier, And what else do I want to do here? Let's increase the speed multiplier just to make this thing run a little bit quicker. And with that, I'm able to press play. I should be able to press play now, and we should see the physics simulations. Let's try that. So there we have it. If I go into side view mode, you can see what's actually happened. The physics simulation, it's still running. We can see in the timeline down here, it's still running, but the thing has stabilized. It has essentially converged to an equilibrium state. So we can hit pause on that. And that would essentially be one form of hanging chain geometry, right? And we could go ahead and analyze that, and in fact we will. But I want to show you actually what happens if we change the main parameter here, which is the vertex mass. So if I change that, instead of it being 0.3, if I change it to 3 and we run that again, so go back to the start of the simulation and let's run that again, you can see that we get our hanging chain hanging much lower, and that's really going to be the main tuning parameter that we're going to use to generate different versions of our hanging chain and analyze each one of them over in our Jupyter notebook. So I'm going to pause that now. So let's say that we wanted to work with this geometry here, right? What I would do, in fact, let's actually do one more. I'll go with 30, and that's going to be the one that we'll sort of run with in this tutorial. So that's 30. We're going to send that back to the start and hit play again. Okay, so you can see it has a significant impact on the shape of the hanging chain. So we're going to just let that come to rest, and it looks like we can stop it there. And so that's our hanging chain geometry. And of course, this is exactly what we would have done, or what people would have done with physical models. You would get a hanging chain, and you would hang it down, and then you would, with very fine measuring equipment, you would then measure the geometry that the hanging chain formed, and then you would use that to inform your further design. We're just doing the same thing digitally here. So what I can do now is I can apply that modifier. So if I come into my modifier stack, I'm just going to hit this button here and hit apply. That geometry is now locked in. So what I can do is I can take this guy and I can rotate it about the X or Y axis by 180, and that is now our grid shell geometry. Okay, so we can write some code in Blender here that uses the Blender Python API to take the coordinates of all of the vertices. If I go into edit mode, we can see them more clearly. All of these vertices, and take the element definitions, which is just the vertex number on either end of an element, and we can export those to a CSV file and then bring them over into our Jupyter notebook for analysis with OpenSees. So if you've taken any of the engineering skills courses where we've used Blender as a modeling tool before, you'll have seen the various different scripts that we write to export this geometry. So I won't write it from scratch here, but I will briefly walk through the various different scripts that we're going to use. And of course, remember, you can download this Blender file with these scripts over on engineering skills. So what I'll do here is switch over to the scripting view, and you can see that I already have a script open here. So what are we doing? We're importing BPY. We need that to work with the Blender Python API. We're importing CSV, standard Python, library, importing NumPy, again standard for Python. Then we're defining OB data, which is a handle to the data for the object, or the object data. Essentially just gives us access to the information or the data relating to this particular mesh object. So next up, we are initializing a container to hold the vertice coordinates, and then we're looping through all of the vertices in the mesh. We're extracting the X, Y, and Z coordinates, packaging them up into a NumPy array in these two lines here. And then if I jump over, we're doing the exact same thing then for the edges. It's just that we're pulling out the vertex numbers at each end of the edge. And then once that's done, we've packaged up our edges, we've packaged up our vertices. We just do a standard file export here where we're generating a CSV file. In my case, that's on my desktop. For you, when you download this Blender file or write this code yourself, you'll obviously change that to your own file path. And if I run that now, we should get some files over on the desktop. So let's give that a whirl by hitting the play button here. Excellent. Okay, so that has generated the following two files. This CSV file over on the left is just the X, Y, and Z coordinate of each of my different vertices in my structure. And then over on the right hand side here, this file is just the vertex numbers for each of my elements. Okay, so these are just the vertex numbers on one end and then on the other end of any given element within my structure. So we'll put those to one side for a second, because there's one other thing that we want to export from our Blender file, and that is a list of the nodes that are going to be restrained within our structure. So if we jump back over to Blender, Blender, we have another script here, which is restraints.py, and this one is doing something very similar. So what I want to do now is, for a model like this, it's pretty trivial to identify the nodes that we want to be restrained. It's going to be this one, this one, this one, and this one here. Okay, so that's just 4 nodes, right? I could just write those numbers down. But for a more complex structure, if you were to have many more points of contact or points of restraint, you could have hundreds potentially. You would definitely want a way of basically selecting them, like box selecting all of the lower vertices, which could select potentially hundreds of vertices for your particular model. And you'll want a script to be able to generate the list of vertices, and that's what this is here, right? So we're doing all of the same imports that we had previously. We are again getting a handle to the data. So this time we are cycling through all of the vertices again, and if that vertex, whichever way you want to say it, if that's selected, we're appending it into our list. Okay, it's that simple. And then we're exporting that list out to a new CSV file, which is on the desktop again, but this time it's going to be called supports. So if I run that now, importantly, you got to run it with the actual vertices selected. So I've got them selected here in my 3D view. So if I run that now, we'll get a new file over on the desktop. Okay, so that has generated the following CSV file called supports. I've opened it up here, and all it really is a list of 4 numbers, right? These are the numbers of the vertices that we had highlighted in our Blender model. So we've got 1, 2, 3, 4. So we now have all of the data that we need. We have the nodal coordinates, we have the member definitions, and we have a list of restrained nodes. This is enough information for us to take over into our Jupyter Notebook and start building an OpenSeesPy model for this structure that we can then analyze and then evaluate. So we'll jump over to our Jupyter Notebook next. Okay, so here we are over in the notebook. Now, instead of writing this notebook from scratch, it's a little bit long, so it's probably going to be quicker and more efficient if I just walk you through the completed notebook here. All right then, so we have our usual, we're just importing all of our project dependencies here at the top. All standard stuff. We've got OpenSees. We're going to be doing a bit of plotting with OpsVis. It's going to be pretty handy for us actually in this project, so it's worth bringing that in as well. We've got math, NumPy. What else have we got? We've got all the usual plotting. One thing that is worth pointing out here is that I have partitioned off some of the plotting code, some of the utility functions over into a separate Python file. So that's this guy here. Now what this actually does is it adds the ability for us to add annotations, 3D annotations onto our 3D plots. And again, if you've taken some of the other engineering skills courses, you'll have seen me do this before, in particular when we were working on our CableNet, 3D CableNet course. I discussed this in some detail, so I won't go through it again here, but essentially we're adding the ability to add 3D annotations and 3D arrows to our 3D plots, which is really handy if you're doing plots of structures. So that's just to say what that is. So we're bringing that in as well. All our plots are going to be controlled by widgets. I like to have a little bit of interactivity with my plots, and so I'll be using widgets. And we've got the dark background because I love a dark background. So that's all of the dependencies brought in. Next up, we are establishing some constants, all the usual good stuff here. We're doing section sizes, cross-sectional area, second moments of area, torsional constant, Young's modulus, shear modulus, material weight, because this structure will be analyzed under its own self weight. We are establishing or specifying a cross-section shape. That'll become important shortly. And then we've got this thing down here called folder name, right? So up to this point, you've just seen me generate one set of geometry, all right? Now, in reality, for us to find what we're going to call the optimal geometry for this grid shell structure, we're going to have to generate multiple different versions of the geometry. And I put that geometry for each different model into a different folder, and I call it model 1, 2, 3, 4. I happen to be showing model 11 here. Let's change that to model 3. That's just a folder name, right? And in the folder called model 3, in fact, I'll show you here. These are all the folders, right? Model 1, all the way down to model 12. And in each of these folders is a set of data. You can ignore force locations, that's redundant, but you've got the edges, the vertices and the supports in each of these folders, corresponding to a different grid shell structure, where we've changed the vertex mass for the simulation in Blender and we get a different geometry. So that's just what's going on there. This is just a quick way for me to jump between different sets of data when I run the code. So let's go back to our main file here, and in fact we can close this guy down. The other thing that to say here is, and this is quite an important point actually, when we think about a hanging chain model, right, we're thinking about a model that is hanging. It's a hanging chain, it's under gravity, under its own self weight, and if all of the joints are pinned, right, in other words it's a true hanging chain, we would expect that structure to be in tension, pure tension. Typically it's a cable net, right? Now if you take that structure and you invert it and you lock all the joints, in fact, even if you don't lock all the joints, if you invert it, it should be the case that that structure then goes into pure compression. Because from the model, from the structure's point of view, all that has changed is the direction of gravity, right? So all those tensile forces would just flip and become compression forces. Now, in theory, that would mean that we should be able to, if there's no moments in the structure, we should be able to model it as a 3D truss structure, where all of the joints essentially are pins. They don't resist moment. And what you'll find if you try and do that is that the structure, the stiffness matrix for the structure becomes singular. And what that means is, what that really means, the physical manifestation of that is that you have rigid body motion within your structure. And really what this all boils down to is, in theory, when you invert your hanging chain, you should get a structure in equilibrium in a state of compression. But the problem when you go from tension to compression is that your equilibrium, which was a stable equilibrium in tension, becomes an unstable equilibrium in compression. And that means essentially you can't solve that structure using a truss model. You have to essentially lock the joints and solve it using a frame model. So this is very analogous to, if you imagine a column, an Euler column. An Euler column will have an Euler buckling load. And in theory, if you increase the axial force on that column beyond the Euler buckling load, it will still be in equilibrium in theory, right? But it will be an unstable equilibrium. And this is often analogized or compared to a ball sitting on top, perfectly balanced on top of a hill. Any disturbance of that ball, it's an unstable equilibrium, any disturbance will cause it to roll down the hill. If you open any textbook on Euler buckling or stability analysis, you'll see this analogy. And it's the same thing maps onto our grid shell structure. In theory, it's in a state of equilibrium when it goes from tension to compression, but that equilibrium becomes unstable in compression, and so we have to essentially simulate the joints being locked for us to solve it using OpenSees. And of course this actually isn't a bad thing, because this is much more in line with what we would actually expect in this structure. If we were to build this grid shell, we would never be producing pinned joints. We would always be locking off those joints, and so they would be resisting moment. And so actually the way we're simulating it much more closely mimics reality. So it's a good way to go. It's not a compromise in any way. So that's a thing that really was worth getting clear in your mind, because if you naively approach this as a truss structure, you won't get very far because the thing won't solve. You won't be able to invert that stiffness matrix. Alright then, so now we've got our constants defined. Next up, we got to import the geometry. Again, sort of people familiar with engineering skills courses will be very familiar with these blocks of code. This is our standard import code where I'm just checking if a particular file exists. If the file exists, I'm bringing it in and I'm generating a NumPy array directly when I'm bringing that the contents of that CSV file in. So we're doing it for nodes, just printing a little statement. If we don't find the file there, we say, hey, stop, the file's not found. And we do that the exact same thing for the edges and the exact same thing for the supports. And so when we run that, we end up with 3 NumPy arrays. Now, one thing I always like to do once I've brought data into a notebook like this is to plot the structure, because it, very often, especially when you're doing it for the first time, very often you will have made a mistake or a bug will creep in your workflow, right, where you think you've exported geometry and you think it should have all gone according to plan, but for some reason something goes wrong, something unforeseen happens between the data coming out of Blender over here and it coming into the notebook over here, and basically what you're trying to do is just verify that everything is exactly as you expect it to be before you get deeper down into the analysis. And so plotting the structure is really good for that. So this is just some standard plotting code here. I'm defining a function that plots the structure. We're using widgets here to control the plot to give some interactivity. So we're defining a plotting function. Fine. We're doing all the standard plotting stuff, defining a figure, adding a set of axes, a 3D set of axes, setting a viewing angle, cycling through each of the members, and this is just us determining the coordinates of the nodes on each end of the member, and then we just plot the member as a line. Very simple. And then we plot the nodes, and we change the color of the nodes based on whether it was a support node or not a support node. And then we have whether or not we want to show the node numbers, and we're adding our 3D annotations, which is coming from that utility functions file. And then we're doing some standard housekeeping, and then let me see, so that's the function that basically generates the plot, and then we use the interact widget to call that function, and we pass in the values of the widgets every time we call the function. So the end result of this is a plot like this, and so sure enough the plot looks exactly like the structure over in Blender on the left, and so everything did go according to plan, right? That's our first hurdle, our first milestone met. We've generated the geometry and we've successfully brought it over into our Jupyter notebook, and we have a nice little visualization of the structure here, and it's controlled by widgets. So I can of course do things like, if I don't want to show the node numbers, to make this a little bit easier to look at, we can just click that off and our node numbers disappear. Alright then, so next up is actually our OpenSees part of the build. So we want to take this data and build an OpenSees model of it. So that's what we're going to tackle next. Okay, so moving on down, we are doing the usual, wiping any previous model from memory. We are then establishing a new model. We're setting the number of degrees of freedom to 3 and the number of degrees of freedom per node to 6. Again, remember, if this was a 3D truss model, that would be 3 degrees of freedom per node, but obviously it's going to be 6 because this is going to be a moment frame. Next up, we are establishing each node within our model. So what we're doing is we are looping through all of the nodes in our nodes array, which was generated by importing the vertices CSV file, and we're calling node here, which is an OpenSeesPy command, and we're passing in an integer, which is going to be the node tag, and then the coordinates x, y, and z for this particular node. Now, next up is the element definition. Now, the element definition, if you're just doing a truss model, the element definition is a little bit more straightforward, but we're doing a model, a moment frame in 3D space, and so it's really important that we're careful about how we orientate, or we specify the orientation of our elements about their longitudinal axis. And that makes sense, because if you imagine an element which has a cross section that is anything other than a circle, right? Let's say it has a major axis and a minor axis, and they have significantly different bending resistances, or significantly different second moments of area more specifically. Well, it's going to be very important that we're careful or deliberate about how we orientate that section about its longitudinal axis, obviously because the bending stiffness changes drastically depending on what way it's orientated. And so in OpenSees, the way you do this is when you're specifying the element. In fact, before you specify an element, you have to specify a transformation, right? A geometry transformation or a geometric transformation. And what that really is doing is it's you saying that you specifying what way that element cross-section is orientated about the longitudinal axis of a given particular element. Now, when we were analyzing 2D models in previous tutorials, planar models, we could just generate one transformation for every single element, because they were on a 2D plane, and their z-axis, which is pointing out of the plane, was the same, or was pointing in the same direction for all elements. But now with this 3D model, this thing has elements orientated in all different directions in 3D space, and so every individual element will have its own geometric transformation specified for it. So what we have to do essentially is, for each element, construct an orthogonal reference frame, an XYZ reference frame local to that element, and then from that reference frame, or within that reference frame, one of the axes is going to be the z-axis for the element, and we're going to use that to generate or to specify the transformation for that element. This is really the only complication. This is the additional headache that comes with doing a 3D model versus a 2D model, right? So once you've understood this, everything else is easy after that. So what's going on here, right? So we are first of all, we're specifying a transformation type. It's just going to be a linear transformation, right? Shapes is just a dictionary where we are storing a cross-section shape for each element. This is purely for visualization purposes later when we use OpsVis to visualize the structure. So this is just for visualization. Don't need to worry about that for now. Next, we're coming on down. We are identifying node I and node j for a given element. We're cycling through all the elements here. We are getting the coordinates, the x, y, and z coordinates for the node at each end of the element. We're using that information to essentially construct a vector, which is going to be the vector along the longitudinal axis of the element. Essentially, it's going to be the local x vector. We are dividing that by the length of the element, which is going to give us the x unit vector, the first component of our orthogonal reference frame for that element, right? The local x-axis. We need now to move on and get the local y-axis. But if you think about an element in 3D space, right? Imagine my index finger going along the element, right? We've got to specify what way, like the y-axis is the next one we're going to build, right? Which is going to be represented by my thumb. Well, what way is that y-axis orientated, right? We know the x-axis is pointing along the element, but that could sort of rotate 360 degrees. And so we have to specify, like, where do we want that y-axis to be? And one sensible thing to do one option would be to say, well, the y-axis is always going to lie in a vertical plane, right? So we can lock the y-axis to a vertical plane. And that's what we do. And we've done that previously in other models in different courses where we've done essentially the same thing, where for each element we've had to construct a local reference frame. And the way we do that is we take the 2 points at the end of an element and we project them vertically by adding 1 to the z coordinate of each of the elements on each of the nodes on either end of the element. That gets us what I'm calling here an I offset and a j offset. So if you can imagine the element, we take the coordinates at each end and we just offset them vertically upwards, right? We then identify a node K, I think I'm calling it here, which is a point halfway between those 2 nodes, right? So that's node K. Now then what I'll do is I will get a vector in that plane. So if we take a vector that goes between node I and that new node K, that is halfway between the 2 nodes that we have projected upwards, we now have a vector in that vertical plane, right? So we've got an x vector along the element. We've got another new vector, right, which is called here vector in plane, right? That's going to be in the vertical plane. Now I want to generate a vector y that is lying in that vertical plane, right? That the two that is defined by the previous 2 vectors, the x and the vector in plane, right? So the local x vector and vector in plane, they are 2 vectors. They can define a plane. I now want another vector that lies in that plane that is perpendicular to the x vector, right? That's going to be my local y. Okay, that's what I'm after here. There's a really neat little way of doing that, which is called the Gram-Schmidt process. It's a geometric operation, and that's the hard bit, right? Once that's done, you're flying again, right? So that allows us to get the local y unit vector. Okay, once we've got that, well, then we can just take the cross product of the x vector, the local x unit vector, with the local y unit vector, and that will give us our local unit z vector. Okay, so at that stage we will have 3 orthogonal vectors that represent the local reference frame for our element. Once you've got that, basically what you can do is, if you look at the documentation for OpenSees, you'll see reference to this thing here, vecxz. The name kind of makes sense, but what that is that is the local z vector for your element. Okay, so we've calculated that, all based on the fact, or based on the criteria we've set, that the local y is going to lie in a vertical plane. Once you've got vecxz, right, the local z vector essentially, you can use that to generate the geometric transformation that's going to be applied to this particular element. So you're in this geometric transformation, you are telling OpenSees, hey, this is the way I want you to orientate this element. And this is so critical because it will have a big impact potentially on the behavior of your structure if you get this wrong. So it's really, of all the code in this entire notebook, if you're into OpenSees or learning OpenSees, the one thing you want to take away and understand is what's happening here. Okay, that's pretty key. So once we've got that geometric transformation for that particular element, we can then just establish or define an element, right? So we're saying it's going to be an elastic beam column element. That's your basic standard flexural element for OpenSees. We're giving it an element tag. It's just a number. And in fact, where do I specify that? There it is there. Look, element tag is n+1. We are then specifying the vertex, or rather the node number at one end, the node number at the other end. We're passing in all of the standard geometric and material properties, and then we're passing in this transform tag. Now the transform tag is going to be just like the element tag here. It's n+1. Okay, so we do that for every single element, and that is how we are establishing our elements. Okay, so that's how we define each element within our structure, and the key thing to keep in mind and to get right is this vec xz, which is really just the local z-axis for your element. Okay then, so with all of the elements established, we come on down and specify the fixity at support. This is very simple. This is just us saying that translational fixity is provided in the x, y and z direction, and there is no rotational fixity about the x, y or z axes. So we're establishing a fixity, and then we're cycling through all of our support nodes or restrained nodes, and we're just specifying a restraint with that fixity for each of those nodes. And with that, our model is defined. And again, a really good idea at this stage is to go ahead and visualize the model to make sure, again, as usual, that it is exactly what you expect it to be. So we come on down. This time, I'm not going to build a custom plotting code. I'm just going to use OpsVis, because all I'm trying to do here is make sure that the model defined within OpenSees, the OpenSees model, is what I think it is, right? So if I was to build my own custom plotting code, I'd end up just plotting what I think the structure is. But the nice thing about using OpsVis is that it's reaching directly into OpenSees and it's plotting what OpenSees has. So it's kind of a nice way of verifying that your OpenSees model is what you think it is, if you know what I mean. So this is very standard stuff again. Defining a new function called plot structure. This time I'm not going to write all the code. I'm just going to call from OpsVis the plot model command. Now I can either plot the model as just a line model, or what I can do is I can plot the extruded shapes for each section. And this is really handy, because this is where you're able to determine if all that work that we did around establishing the z vector for each of our elements, this is where we work out if that all worked properly or not, right? Because we'll be able to visualize and see the actual cross sections extruded along each element. So I'll control whether or not we view that version of the model or the line version of the model with a simple flag, which is going to be called show sections. And then we're just doing some standard plot tidying up. So when we come on down, you see, this is the model that we get. This is the OpenSees model. We've got all of our nodes, all of our elements. We've numbers shown for all of them, because I think I've got the flags set to show labels, or element labels here and node labels here. But if I switch my show sections flag next, right? So if I hit this guy, we can see we now have the sections. So remember what I said when we were establishing the orientation of each of these sections. I wanted the local y-axis to lie in a vertical plane. That means if I look down on top of this structure, for each of those elements, I should just see the narrow side, right? They should all be sort of aligned vertically, right? There should be none of them at a sort of a skew angle, right? So if I can confirm that by basically coming in here, changing my rotation to 90, I'll change that to 0, and there we have it, right? So we can see all of our elements, all of our sections are aligned vertically, okay, with the narrow face being visible from the top. So you're not seeing any of the side faces of each of these elements, and that's what I specified. Now, that is just one possible way you could specify the orientation. Depending on the structure you're analyzing, you may choose to have a different orientation. It's entirely up to you, but that was just one simple way of having a uniform orientation for each of our elements. So all we're saying here is it has worked, and it is as I expect it to be, which is what we want to see. So next up, we can come on down to the loading. So the loading for the model is going to be very, very straightforward to establish or to determine. We are going to define a time series load pattern. These are two standard lines I seem to end up writing every single time. At some point in time, I will do something a little bit more complicated and explore the other possibilities here. But for what we're doing today, this is fine. Now, the loading is going to be self-weight. And that's important because the geometry of our structure was established for self-weight, essentially a hanging chain, and we just then inverted it. So we would only expect that structure to be in a state of equilibrium under its own self-weight. Of course, we've locked all the joints now, so it could take, you know, point loading at arbitrary locations potentially as well. So what we'll do is we will assume, let me see, what am I doing here? I'm establishing a container to hold all of my nodal forces. I'm cycling through each member. I am extracting the length of the member. I'm using that to determine the self-weight of the member in newtons, and then I'm assigning that for half of that force to each of the nodes, right? And if I do that, if I cycle through all of the members and I do that for each member, what I end up with is an accumulation of self-weight on all of the nodes in the structure, which I can then, in the next block down here, go ahead and apply to each, you know, in the negative Z direction to each of my nodes. So that's what's going on there. Then we can come on down and visualize the loads on the structure. Again, you'll kind of notice a theme here. Whenever I've done something, I'm trying to visualize what I've done because it's just a great way of verifying that everything has worked and I haven't made a mistake somewhere. So, for example, I come on down here, right, and I want to plot these loads. I want to visualize them. So what I'll do is, again, I'll use OpsVis, but I will modify the OpsVis code, right? So I'll say, right, plot the model, but in addition, I want to plot a force arrow representing the force on each node, and I want the length of the arrow to be proportional to the magnitude of the force. And again, this 3D arrow is one of the additional utilities that's coming from our utility function here, or our utility file here. So when we have a look at that, we can see we're back to our custom plot of the structure, and we also have these force arrows coming on. So you could rotate that around and you could have a look and, you know, investigate. But the thing I'm after here, the thing I want to verify is that there's essentially 3 different arrow lengths here. We've got the smallest one at the being applied at the points of support, because there's only 2 members contributing to that force. We then have a mid-level, let's call it, arrow length, which is going to be all of the arrows along the perimeter. And again, that makes sense because there's only 3 members contributing to that force. And then we have a 4th arrow length, which is going to be all of the internal forces, because we have 4 elements contributing to the force on every node. So again, it's another way of us looking at it and saying, okay, yes, that makes sense. We can move forward with a greater level of confidence. So for example, if I looked at this and I thought, well, you know, let's say these were all different lengths, for example, well, then I'd know something went wrong, right? And so I'd have to go back and make sure I worked out what the problem was. But no, everything here looks intuitively correct, so we move on. So the next stage is the analysis, and again, the analysis steps for a relatively straightforward, linearly elastic, static analysis like this. It's all the exact same steps which you will have seen in previous tutorials, previous OpenSeesPy tutorials. So I'm not going to step through all of these again. Again, refer back to some of our previous tutorials where we've kind of talked a little bit more through this. Once you run this, if you get a little 0 reported out here, well, that's good news. That means that the model worked, or rather the model was solved successfully, and we can go ahead and start investigating the results. So the first thing I like to check is the deflected shape. We'll again use OpsVis here. We could do a custom version of the deflected shape, custom code, but for something like this, OpsVis is fine. It's a little bit limited, but it gets us 95% of what we want. So this is again fairly standard stuff. We're just passing in a few flags. So what I'm saying here is, if I have the scale manually flag set to true, well then the scale of the plot, of the deflection I should say, will be based on whatever I set the scale factor to. Otherwise, we will just let OpsVis decide what an appropriate scale would be for that deflection to be visible to us, right? So that's the only real flag that's happening here. This is all standard plotting, and this is our usual widget setup. So here we have it. We have scale manually is set to off. So OpsVis has, in its wisdom, decided that an appropriate scale for us to be able to see what's happening, an appropriate scale applied to the deflection is 11,560, and that's fine. But if I was to come in here and let me see, if I was to change that to scale manually, and if I change that back to, let's say, 100, so we can see that there's negligible deflection, or it's imperceptible. Change it to 500. So this is what I like to do. I like to kind of, you know, apply very little scale to the deflection and sort of slowly creep up to see where I start to see it. We start to see it at around 500 and at about 1000. it starts to become, noticeable. So it gives us a good sense of the magnitude of deflection. What we can say with this is that the magnitude of deflection is really, really small. And that's good news, because this was a linear analysis. If these deflections were really big, well, then we'd have to start thinking about things like geometric nonlinearity, but we clearly don't have to in this case because our deflections are really, really small. So that's good news. So once that's done, we're happy with our deflection. And again, the other thing that we're looking for with our deflection actually is that it makes sense, right? It's intuitive. Well, one of the things we would like to confirm is that it is symmetrical, and it is symmetrical. It's a symmetrical structure that is symmetrically loaded, and we would expect, therefore, a symmetrical deflected shape, which is what we see. So again, we're always looking for these little telltale signs or red flags. The absence of red flags is obviously a good thing, right? So there was no red flags with this, so we can move on. Next up, reactions. I'd like to know what the reactions are. So we're just going to execute this OpenSees command to calculate the reactions, and then I'll just set up a little loop here that prints out the reactions. Again, what am I looking for here? I want to make sure the reactions are symmetrical, I suppose you would say, but essentially the vertical reaction is the same for all of our nodes, and the magnitudes of the X and Y direction reactions are the same, but that the directions make sense. And you can go through each of these, node 1, 2, 3, and 4, and confirm for yourself that the direction of the X and Y component of the reaction force is correct. In other words, it's pointing back in towards the center of the shell. So the next thing we're going to do is visualize the axial force distribution, and this is where the plots start to get a little bit more interesting. So to visualize the axial force distribution within our structure, all we're going to do is plot the structure again, but this time we will map the color of the individual members to the axial force within that member. And to do this, we set up a simple color scale. We can add a color bar associated with that color scale, and that'll give us a really nice visualization of the distribution of axial forces in the structure. The first thing that we need to do in order to implement this is extract the axial force for each member. Now this is pretty straightforward. All we do is cycle through each of our members here and extract the axial force for each one by using the basic force command from OpenSees, and then we can store that axial force in this array of axial forces, and this is going to give us all the information we need. So if you think about it, we're really just using the plotting code that we use at the very start of this notebook to plot the structure. The only thing that's different is that we set up a color scale based on the range of force values, and we map the color of the members to that color scale based on the force in the members. So the code is here. I won't step through it in detail because 95% to 90% of it's the exact same as what we had before. Now, one nice little additional thing that we can do, it looks like a lot of code, but there's not a lot of new stuff happening in there. One nice thing we can do is, well, if we just see the structure first, this is our structure with the axial force distribution, and of course we have our range of forces, and noting again that they're all compression forces, all the numbers are negative, and so the whole thing is in compression, which is exactly what we would expect. So we're going from if we look at the actual force distribution itself, naturally enough we see the largest magnitude axial forces down in the members adjacent to the supports, because if we think about it, all of the force is being funneled down the load path essentially is down towards the foundations, and it's those members that are taking all of the forces down into the foundations, and so the intensity of axial force is increasing as the number of members that force is distributed across is reducing. Interestingly enough as well, we can see on our perimeter members here, these are all experiencing larger magnitude axial forces than the internal net members, I suppose you might call them, and they're behaving to a certain extent as four individual arches, and they're what's essentially taking all of the force from the internal members, comes down into our perimeter arching members, and then works its way back down into the supports. So you look at this, and the first thing you might think as an engineer, you look at this and you'd say, well, it probably makes sense not to have the same cross section used for all members, right? It would probably make sense to have larger cross section members down here around the perimeter, and then lighter cross section members in here. And in fact, that would be a really good exercise to do for you when you get this notebook. Modify it, right? Modify it so that you can have different cross sections and start playing around with applying different cross sections to different members based on the force distribution, and iterate on the structure that way. That would be a really nice addition to this particular notebook. So one other thing that we can do here, again, that's that's slightly a step beyond what we've done previously in the previous plotting, is that we can control the range of our force scale, right? So currently the force scale is set to be, the extreme values of the force scale are based on the extremes within the range of force values. But what we could do is we could artificially change that. So if I wanted to, so that's what I've got here with this this force slider. So if I was to change that, so it's like minus 90, if I wanted to identify a range of elements that experience a force within a given range, I could set this to, let's go with minus, we already have a minus, let's go with 20. All right, and run it again, and we can see that the force scale is updating, and now all we're seeing is members within the structure that have a force within that range, and all of the other members are just dashed lines. Like, it's a simple little thing, but this is why I really like building these things from scratch, because you can build in whatever your imagination can come up with in terms of what you want to see within the structure. You can just build it. So this is just one little thing that you can do that sort of adds a little bit of extra insight, or will give you a little bit of extra insight into the behavior of the structure. So that is our axial force distribution, and again, it looks like a lot of code, but to be very honest with you, the vast majority of that is just a standard plotting code, and then the extra bits is just creating a color bar, or a color scale, and then a color bar associated with that scale, and then mapping the color of each member to that color scale based on the force in the member. Alright then, so again, download the code to dig into it in more detail yourself. Next up, okay, so this is a moment frame, right? We've said that we've talked about why we couldn't model this structure as just a truss, and it needed to be a moment frame, and that means that there's potentially going to be, well, there will be bending moments in it, and we're going to want to visualize those. Now, to visualize bending moments on a structure like this is a lot more involved than it is to just plot the axial force distribution, because obviously we can't map a single color to a single element, because an element will have a variation of bending across that element, across the length of the element, and so you'd have to do a bending moment diagram, which is not impossible by any means, it's doable, but it's just a lot more involved. So what we can do is revert back to OpsVis, and it has a great little function here which allows us to plot the moments, the axial forces. I don't like its axial force diagram, that's why I built my own, but it's really handy for visualizing the moments, right? So what I'm looking at here is a command, section force diagram 3D, and I'm passing in NZ, so that's going to be the major axis bending moment for the elements that we're going to visualize. So when I run this, we get a bending moment diagram. Okay, so you can see bending moments within the structure. You can see that the larger bending moments are in the perimeter members, and more specifically down near the supports. And the members that are in the vicinity of the supports, those are the members that are seeing the largest bending moment. This is a really nice way of qualitatively visualizing it. It is not fantastic for visualizing individual values, because the structure is relatively dense and you get values printed on top of each other, which is the usual problem you have when you're trying to plot a bending moment diagram. You get values at each end of each member, which means you get text values for a moment overlapping each other at nodes. So I haven't bothered to print out the actual values, but what you can do is you can say, right, well, I can identify visually where the largest moments are occurring, right? So it's down in these members coming down into the supports, and it'll be in the member that connects to the support. So what I could do is I could identify the member number by the element tag, and then I could extract the moments for that member in particular, and that's what I've done here, right? So I've written a little function that's called report actions. We can pass in an element tag, and it will just go through and print out the various different moments. Turns out that one of the element tag for one of those members that joins into the support is element tag 2, so we can pass that in, run our function, and we can just get a snapshot of what the moment distribution is, what are the various different moments at each end of that element, and we can see. And we can obviously get the axial force as well. So we see a 92 kilonewton compression force. We've got major axis bending about the z-axis. So we've got minus 404, minus 45. Interestingly, we also have let's call it a significant moment about the minor axis, right? So essentially this member is experiencing some relatively significant biaxial bending, right? And if we're going to go ahead and design this thing, that is one thing that we would need to consider. You know, we want to consider biaxial bending, the stresses developed as a result of that, and then in combination with the axial stresses developed from the axial force. So a lot of information in here that's going to be really helpful from a design point of view. But at this point in the analysis, right, think about what we've done. We've analysed a single geometry, okay, so we've got all of the information about how that particular structure behaves, but if we kind of go back to the very start, that all stemmed from a particular geometry that we generated over in Blender, right? So this structure here, if you remember, was generated by specifying a vertex mass of a given value, some arbitrary value. We set it to 30, I think. Now, that's just one possible geometry, and the whole idea here is that we want to identify a structure, the optimal structure, right? And that then raises the next question, which is, well, what's optimal? How would you define optimal? And there are a number of different ways we might think about this, but one reasonable way that we might approach it that is quite straightforward, and it's still directionally correct. We could say that optimal is the structure that experiences the lowest bending or the least bending, okay? Because obviously we want to struct bending is an inherently inefficient way to use your cross section by comparison to axial force, because in axial force the entire section experiences the same magnitude stress, but in bending or normal stresses due to bending we have larger stresses at the extremes of the section, and they vary linearly, as you know, for a bending stress distribution. So we might say to ourselves, well, the optimal structure would be the structure that experiences the lowest bending stress. Okay, that's a reasonable step forward. And so the thing to do, if we wanted to identify the optimal shape, the shape that experiences least bending, would be to generate a number of different geometries. How would we do that? Well, we just run the same Blender physics simulation and we would change the vertex mass in each one, and that would give us various different geometries, and then all we'd have to do is run the analysis for each of those and extract, determine the bending stress in each one, and then identify the one that has the smallest bending stress, and then you're done. Okay, so you've identified, according to your definition of optimal, you've identified the optimal structure, and that's the approach that we're going to take here. Now, again, that ignores biaxial bending. Well, it ignores minor axis bending. It ignores biaxial bending, the interaction between bending about both axes, and of course axial force and the distribution, or rather the combination of axial and bending stresses. So there's a lot going on to be aware of, and we're just focusing in on one potential definition, but it's a reasonable approach, so we'll move forward with that. So to do that, what do we have to do? Well, we've got to determine the bending stresses for each of the elements in our structure, right? So to do the bending stress, we just use the engineer's bending equation. So I've just got a little function here that cycles through each of our members. We are going to calculate the major axis bending that's the major axis bending moment at one end of the element, the major axis bending moment at the other end of the element. We will take the maximum of the absolute of those two values, right? So we don't worry about if one is negative and one's positive. We just want the absolute maximum, and we will then calculate a maximum normal stress as a result of the maximum bending moment, right? And this is just your engineer's bending equation, sigma equals my over I, and that gives us a stress. We want the absolute value of that stress, and we're going to then store that. So once we have that, well, a nice thing to do might be to plot that, right? So we could come on down and, using pretty much the exact same code that we had to plot the axial force distribution, we can plot the bending stress distribution, and that's what we have here. And naturally enough, it pretty much mimics what's going on with the axial force distribution, right? We can see, I suppose in the broadest of terms, we can see that the larger magnitude stresses are being experienced down adjacent to the supports. And again, we can do the usual tricks where we can change the range of values that we're visualizing. And of course, if we start only focusing on larger magnitudes of stress, we'll only see stresses down here. So for example, if I said I only want to know about, or I only want to see which elements are experiencing a stress between 0.2, what's the scale, between 0 newtons per millimeter squared and 0.3 newtons per millimeter squared. Again, you look at that and you say 0.3 newtons per millimeter squared, that is not a lot. So there's scope here to dramatically, I would say, reduce the cross-section size. Obviously we would have to keep an eye on deflection as well, but we're not really significantly stressing these elements at a maximum stress of 0.3. So okay, so what we could do is let's just see. Obviously I'm gonna, if I change this to 0.2, we'll see just the areas around the supports light up. So in that way we can kind of focus in and we can see, yeah, that's where the maximum bending stresses are occurring. All right, so far so good. What do we want to do though? We need some metric, right? We need some particular value that we can use to judge the efficiency of the structure. And the simplest thing to do is to simply just say, okay, for a given structure, what is the maximum value of the major axis bending stress across the entire structure. Okay, and that's what we can do here. I've just put it into a statement and printed it out. But what we're doing is we're taking the maximum value of the range of stresses we've calculated, we're rounding it off, and we're saying then that it's 0.269 newtons per millimeter squared for this particular structure. Okay, great. So we now have something we're going to vary, right? We're going to vary the vertex mass in Blender used to generate geometry. That's okay. We then have another value that we can attach to that particular parameter, right? So we have a thing we're changing, we have a result which quantifies the efficiency, if you like, of that particular version of the structure. So what we can do now is generate some geometries, determine the maximum stresses that develop, the single value of the maximum stresses that develops, and then essentially just plot them and see, or we don't even have to plot them, we can basically just put them in a table and see where the local minimum is. So the way I've done this in this particular tutorial, in this little build, is very simply. So I've gone ahead and I have created, in fact, if I jump over to our tutorial, it's probably an easier way to visualize this. So here we are over in the tutorial, for the written tutorial for this particular build. So if it's a long one, it's like a 47-minute reading time because it's quite detailed. But if we go all the way down, so here we are here, right? Let me zoom in here a bit. So what we can see is that I ran, first of all, 4 simulations. I ran one with a vertex mass of 0.3, then 3, then 30, then 100. And that's to give me a kind of a broad view of the parameter space, if you like. And then the maximum value of MZ, that should actually be sigma Z. I must change that. That should be sigma Z max rather than MZ max. It's going to be 6.3, 1.6, 0.29 and 0.99. So we look at this and we say straight away, oh, okay, the optimal shape is going to be associated with a vertex mass somewhere in the region of 30 kgs, because we see a local minimum here, because we've got a higher value here and we have a higher value here. So what we can now do is do a second round of analyses, a second round of physics simulations, where we zoom in on the geometry around the 30 kg mark. And so that's what I've done. So then I come in and I say, right, all we're doing here is we're hunting for the minimum essentially of this function, you could say. All right, so we're going to run sims for 20, 25, 30, well, we already have 30, but 35 and 40, and then we essentially tabulate the values of maximum stress. And again, we see, right, we're going 0.345, 0.31, 0.29, 0.279, so we're still going down, and then we're going back up at 0.309. Okay, so we now have zoomed in a little bit closer on where the optimal geometry is. So we do another round, right? You keep doing this as long as you like, but this is the third and final round, right? So I've then done sims of 33 kgs, 34 kgs, 35 kgs, 36, 37. You get the idea, right? So it ends up that we can identify a local minimum here at around 36 kgs. In other words, if I set the vertex mass in my Blender physics simulation to 36 kgs, that results in a geometry that, when I then go and analyze it, produces the lowest level of bending stress about the major principal axis for my structure, and based on my definition of what optimal is for the structure, that's going to be the optimal geometry because it minimizes the bending stress, and that essentially, in a nutshell, is it. So we could automate this process. We could dive in and make it a little bit more complex. We could explore different criteria for what optimal looks like. We could look at the ratio between axial stress and bending stress. We could dig in more, I suppose, and we could start looking at criteria around biaxial bending and relating biaxial bending to axial stress. So there's all sorts of different criteria that you might use, but I tend to sort of think about this in the following way. This is like an engineer's solution, right? Not a mathematician's solution. Okay, so this is how as an engineer, if I was looking at this and I was tasked with analyzing this is how I would get my first approximation. I would do something that intuitively makes sense. It's going to be directionally correct. It's going to get me in the ballpark, and it's going to get me 90% of the way there. You could then iterate on this and come back around and look at a more complicated solution, a more elaborate solution, and knock yourself out. But this is going to be in the right ballpark. So that's it, right? That's the pipeline. That's the tutorial. So the next question from here is what's next? Where do we go from this? Because this is part 2 in a series that looks at gridshell structures and form finding in particular. So this was an unstrained gridshell. What I really want to do, and what we're going to be doing in the next tutorial, is focusing on strained grid shells. Those grid shells that start out as a flat grid and are essentially pushed or bent up into position. And of course, that process of bending them up into position or lifting them into position induces stresses within the structure. And we want to be able to capture those stresses. And of course, those stresses are directly related to the shape that that structure will take. So that's going to be a really fascinating problem, I suppose, to get ourselves stuck into. So that's going to focus on a technique called dynamic relaxation. So in the next tutorial that's going to be coming in a little while here, we're going to be building a dynamic relaxation algorithm, and we're going to be using that to do our form finding rather than physics simulation in Blender. So I'm really looking forward to that one. So I hope you found this one helpful. I certainly enjoyed putting it together. As I say, there's plenty of additional resource on the Engineering Skills website. There's a full write-up of this, and then all of the code and Blender file, etc. can be downloaded as well. So head over there and grab that and dig into the code yourself and start playing around with it and seeing what you want to tweak, what you want to change. And by all means, what I would say, the obvious thing to do is repeat this entire process, but do it for a more elaborate cutting pattern. We've just done a 10 by 10 grid, right? So come up with some funky different shape grids, run them through a physics sim, do the structural analysis, and see where you end up. So that's it for this one. I'm going to leave it there and sign off, and I will see you in the next one.